couple quick examples of the polar form of a complex number. It's really this is really converting rectangular to polar, but just the notation's a little different. And it's always good to get practice with that. So suppose we have a complex number 2 minus 2 root 3I. And so let's see, what is that? If on the picture here, it's got real part 2. Oh, you know what? I need to probably shrink this in a little bit, zoom this in. Okay, that's good. Real part 2, and then a negative, let's see, 2 root 3. Root 3 is like 1 point something. Maybe this is like about 3. Something roughly around here. Something roughly about 2 minus 3i. Okay. And instead of focusing on the real part and the imaginary part, essentially the x and y coordinates in the complex plane, we want to get the r and theta. Okay. So we want to find the magnitude of z, which is just the r, and arg of z, which is the theta. Okay. Well, that's always what we always do for polar. R is the square root of a squared plus b squared. That's just always a universal formula. It's just Pythagoras applied to going a this direction and b this direction. And so it's going to be the square root of 2 squared plus 2 root 3 squared. Remember, it's always plus. Even though this is a minus, even though this is an I, it's just this distance, and they're squared. There's never a minus in here for us. And what are we going to get? We're going to get the square root of 4 plus 4, which is 2 squared, and then root 3 squared is 3, so it's going to be 12. Oh, hey, that's a nice number, 16. Oh, it's a square root of 16, rather. And so that's 4. Okay, so this was a little contrived to make this number nice, but that's okay. So there's the magnitude, okay. And what about the argument? Well, that's a little trickier. We look at the tangent of theta, and that's always b over a. And that's equal to minus 2 root 3 over 2, which is minus root 3. And then we really need the arctangent, the inverse tangent of that. Well, we actually know this value as a value of tangent. This is where it's really nice to have those values of tangent memorized separately. If you're always doing them as sine over cosine, you're not going to recognize this very well. That's exactly where theta is equal to, well, let's see. This is a negative angle, and clearly we're down in this quadrant. It's very important to get the quadrant information right at the start. That's one reason I drew this. So we're going to have a negative angle cranking clockwise from the x-axis, and it's the steep one, because this is bigger than 1, and so that's going to be minus pi over 3. Now, how do we write this? Well, we introduced today a nice way to write this. We say that not just the r is this, the theta is this. We write it as z, the complex number. Let's put this display. Equals, and we take r, and we take that times the quantity cosine minus pi over 3 plus I sine, plus I sine minus pi over 3. This is really nice because it tells us sort of both forms all at once. By just writing it in this form, that's r displayed as the magnitude, and this is the theta. So remember, cosine theta plus I sine theta was a way to put a complex number with the right argument, but put it on the unit circle, so it has magnitude 1. Then the 4 just scales that up, so it has magnitude 4. And so that visibly displays the r and the theta in the form, but if you want to actually get the a plus bi, you just actually have to evaluate the cosine, evaluate the sine, and then just multiply everything by 4. So it tells you both forms at once in a way. And an abbreviation for this that people often use is 4 cis of minus pi over 3. And that's fine. Cosine plus I sine. That's the cis. Okay. So let's do one more example. Let's say z equals minus 4 minus 2i. Oops. Okay. Now we can still get the magnitude of z. Oops. No, that's not what I wanted. There we go. Magnitude of z is the same formula, square root of 4 squared plus 2 squared. And that's not as nice anymore. It's the square root of 20, which is 2 root 5. Okay? And then the theta, tan of theta is still b over a, and that's now equal to 1/2. Now that is not one of our nice values. That's a nice value of sine or cosine. It's not a nice value of tangent. And so is it true that theta is just inverse tangent of 1/2? Think about that for a second. Of course, the fact that I asked you, it probably means the answer is no. And it is indeed no, because where is this? Let me zoom in a little bit, or zoom out a little bit here. This guy is minus 4, 1, 2, 3, 4, minus 2i. That's in the left-hand quadrant. It's in quadrant 3. That's never going to come out as a value of inverse tan. And this thing that's annoying about converting to polar theta is still here. That's going to be plus pi. Because let's actually calculate this numerically. That's 0.5, about a half a radian. That's somewhere in here. It's positive, and it's not anywhere near, not bigger than pi, certainly. And so we have to add pi to that. And so let's go ahead and add pi and compute numerically again. Okay, so that's the actual radian value. So now our actual complex number z, no, that's not Greek though, is going to be 2 root 5 times cis, I'll use that abbreviation, of this weird, funky number in radians. That's what it is. It's not something with a pi in it because this wasn't a particularly nice, a nice value of tangent. So that's a definitely more complicated answer, but it's still the same idea. And it still tells you the radius, the magnitude rather, and the direction, the argument. And then if you actually just crank this out, expand it to cosine plus I sine and plug it in, it'll give you the a plus ib form back without having to know where it came from.